Hey everyone, I hope you're well. I look forward to talking with you either in our interactive class time, or you're always welcome to make an appointment with me, a virtual meeting. Um, as you know, I'm going to be making some videos like this for lectures. I've never done this before, and I'll be honest with you, making these videos is actually much more terrifying than standing in front of you in person for some reason. But I'm going to do my best, and if you have suggestions for how I can make these better, please let me know, and we can work together, and they'll get better as we go on. So today we're going to start on chapter 5 in your book, which is on mathematical induction. So today in this video I'm just going to give a basic introduction to the idea of induction, and then in some subsequent videos we'll do some examples. So if you think back to when we talked about propositional logic, we said, for a bunch of different types of propositions, we said, how do you prove a proposition of that shape? So in particular, we looked at to prove, if you wanted to prove a proposition of the form for all x, p of x, then you can assume that x is some arbitrary element of the domain, and then you prove p of x. But sometimes this is not good enough, and so induction is another technique for proving for all type of statements, in particular ones that are for all natural numbers. Okay, so sometimes when we want to prove a statement of the form for all natural numbers n, some proposition holds of n, then we can use induction. So what's the idea? So to prove this for all statement, conceptually, I have to prove infinitely many propositions, right? We have to prove p of 0, we have to prove p of 1, we have to prove p of 2, p of 3, and so on. And I can't literally write down infinitely many proofs. But here's something that I could do. I could start by proving that p of 0 is true. Okay, but then instead of literally proving p of 1 and p of 2 and p of 3, I'm going to prove something else. I'm going to show, use a color. I'm going to show that each one of these implies the next one. So for any number, if the proposition holds for that number, then it'll also hold for the next number. So I set up this big chain, and if every item in the chain implies the next one, and we also have shown the first one holds, right, then everything in the chain is going to be true. So that's the basic idea of induction. You can think of it like setting up an infinitely long chain of dominoes, where the first domino corresponds to p of 0, and so proving p of 0 is like knocking that first domino over, and then right, we're going to show basically that each domino is going to knock over the next one, and the next one, and the next one. Okay, so first, proving p of 0, this is called the base case, or I think your book calls it the basis step. So let's say or basis step. And then, right, these yellow arrows here correspond to what's called the inductive step. Right, and for the inductive step, I want to prove that for any k, P of k is going to imply P of k plus 1. Okay, so no matter what k is, if P of k is true, then P of k plus 1 is also going to be true. And then, of course, that will imply that P of k plus 2 is true, and so on. And then we conclude that this proposition will be true for all natural numbers. So, formally, let's write down a formal statement of induction using propositional logic. Sometimes I think it's helpful to be able to explicitly write it down formally. Usually it's not presented that way, but so formally we need to show P of 0 is true, that's the base case, and right, for all natural numbers k, if P of k then P of k plus 1 holds. Okay, and all of this together implies that P is true for all natural numbers n. Okay, so again, this is our base case, P of 0. We can show P of 0, and for any number k, if P of k, then P of k plus 1. Right? Just like knocking down a chain of dominoes, this will show that P is going to be true for every natural number. In the next video, we'll do a couple examples.